Deepak, sir. Good morning, sir.
Yeah, good morning, madam.
So I will just give a brief intro about you and then we will start the session, sir.
Yeah, no problem, no problem. I think
Okay.
the number of participants 14 right now. Yeah, by the time they can
Yes,
also
sir. They
join.
are
Yeah,
good
yeah,
to join.
yeah.
Okay, sir. A warm good morning to all. It gives me immense pleasure in welcoming a renowned resource person, Dr. Deepak Ranjan Nayak. We welcome you, sir.
Thank you, ma'am.
He is going to deliver a talk on advances in machine or deep learning for medical image analysis and classification. Here is a brief introduction about Dr. Deepak Ranjan Nayak. Dr. Deepak Ranjan Nayak is an assistant professor at Department of Computer Science and Engineering, Malaviya in the National Institute of Technology, Jaipur, India. Prior to this position, he was an assistant professor at the Department of Computer Engineering, SV National Institute of Technology, Surat, India. He worked as a postdoctoral fellow at Indian Institute of Information Technology, Design and Manufacturing, Kanjipuram, Chennai. He received his PhD degree in Computer Science and Engineering from National Institute of Technology, Rourkela, India. He has published over 40 articles in peer-reviewed journals and conferences of international repute. His current research interests include medical image analysis and classification, machine learning, deep learning, pattern recognition, and computer vision. His publications have more than 600 citations, H index of 13 and I-10 index of 15. One of his papers was included in ESI highly cited papers. He has received international travel support from Department of Science and Technology DST, Government of India in 2017. He has also received the Outstanding Reviewer Award by Computers and Electrical Engineering Journal Elsevier for the year 2017. He serves as a reviewer of more than 40 peer-reviewed journals such as IEEE Transaction on Circuits and Systems for Video Technology, IEEE Journal of Biomedical and Health Informatics, IEEE Bar ACM Transaction on Computational Biology and Bioinformatics, Scientific Reports, IET Image Processing, IET Computer Vision and Image Understanding, Pattern Recognition Letters, Computer Methods and Programs in Biomedicine, Biomedical Signal Processing and Control, etc. He has also served as technical program co-chair and committee member of several conferences of international repute. He is a member of IEEE. He serves as a guest editor of Mathematical Bioscience and Engineering Journal. Sir, I welcome you to deliver the talk on the topic Advances in Machine or Deep Learning for Medical Image Analysis and Classification.
Thank you so much, ma'am, for the kind introduction. Madam, can you please check whether my screen is visible or not?
Yes, sir, it is visible, sir.
Even am I audible, right? Clearly.
Okay.
So can we start right now?
Yes, sir, you can.
Yeah. Thank you so much, ma'am. Hello, everyone. Very good morning. So my name is Dr. DEEPAK RANJAN. I'm a faculty at Department of CSE, Malaviya National Institute of Technology, Jaipur. So what I'm going to discuss today is advances in machine or deep learning. So I will discuss, a little bit about machine learning and mostly focus on deep learning for medical image analysis and classification. So how machine learning and deep learning technologies are helpful in analyzing medical images, and that will be helpful to the doctors that will see. And so throughout the discussion, I will focus on these points. So what is biomedical image processing? What do you mean by biomedical imaging? What are the different types of biomedical imaging doctors and radiologists are using right now? And machine learning based CAD system, deep learning based CAD system, what are the difference between machine learning and deep learning? When to apply machine learning, when to apply deep learning? What do you mean by CAD system? So what are the advantages of CAD system? So what was the problem with the manual interpretation? So that we'll see. And also I will list out some of the current challenges in this particular field. And I have chosen three different problems which I will discuss today. Multi-class brain disease classification using MRI, magnetic resonance imaging, diabetic retinopathy using retinal fundus images. Diabetic retinopathy is a kind of eye disease basically caused because of the diabetes disease, and we'll see one by one. And last but not the least, the COVID-19 screening, a very important thing, how the machine learning and deep learning technologies are helpful in detecting or diagnosing this COVID-19 screening, we will see. So we'll start our discussion today with what do you mean by medical imaging, and why it is important. We'll see. So, medical imaging is the process of creating digital visual representation of the interior of the body for clinical analysis and medical intervention. So, the definition itself says that it's a process of creating digital visual representation of the interior of a body. So, that is why the medical imaging is very, very important. In earlier times, what happened is the doctors used to go for operation in order to know that what exactly happened to which part of the body. So they have to cut some part of the body to see that what exactly happened to that particular part of this body. But this medical imaging technologies, and here I have listed out some of the technologies which are commonly being used by the doctors and radiologists, which are nothing but X-ray imaging, magnetic resonance imaging. The short form is MRI, electron microscopic imaging, ultrasound, CT scan, PET scan. Here are some of the medical imaging which are actually extensively used by the radiologist. And apart from that, also there are some medical imaging technologies. But the most important thing here is this helps in creating digital visual representation, and that's what our machine wants. So what we really want here is we want to enable a system that will help in deciding that whether the person is having some disease or not, and ultimately that will assist the doctors to take the reliable decision. So once the output is in the form of digital, so what computer can see? So if you are seeing, if you are looking at one images, but computer looks at images in forms of numbers, array of numbers. So this is what the job of the medical imaging is, and the output is nothing but in the form of digital visual representation, so which can be easily processed by the digital computers. And you can easily apply the techniques like machine learning, the cutting edge AI technologies, deep learning in order to process them. So here are some of the examples or samples you can say from each of these categories, which I have listed out here, just to show you that how the output of the different biomedical imaging looks like. And if you see in the first row, there are three images over here, and which are nothing but X-ray samples. You might have experienced these images in your lifetime, because this is very common, X-ray images. So first one is nothing but X-ray image of a palm. The middle one is nothing but X-ray image of a chest, and the last one is nothing but a mammogram image, X-ray image of a breast. So, and why it is coming like, why the output of this X-ray is always coming like black and white sets, that also we'll discuss later on. And what are the advantages, what are the merits and demerits of X-ray imaging, we will discuss later on. So just for now, I would like to show you that how the samples of different categories looks like. So if you see the images which are in the middle low are nothing but MRI scan images of brain as well as the spine. And the last one is nothing but, if you can see, there are three different images which I've shown, which are nothing but microscopic images physically used to detect the blood cancers like leukemia. And here you can see there are blood cells, round red cells, and there is something called nuclei present over here. And coming to other varieties, ultrasound, very popularly known. And there is something called a CT scan. I will also discuss in detail how the images are generated and what you mean by the slices here. And there is something called as PET images. So apart from this, there are also some other varieties of biomedical imaging technologies. Yeah, so we have already discussed about the importance of biomedical imaging, and which is nothing but it enables the doctors to see inside a patient without having to cut them open. And as I already mentioned that I am a computer scientist, so maybe some people are from electronics background, electrical background, mechanical background, biotechnology background. So why we all are here? Because this is the reason, the medical imaging is the reason why we all are here. It brings the scientists from different field in order to come up with a very good solution. So this is what the importance of biomedical imaging is. And coming to the definition of biomedical image processing is very easy. Like we know the definition of the informal definition of digital image processing. So we simply call it as like processing of images by means of a digital computer in order to extract some meaningful information. So here it is also similar to that. It is nothing but the processing of biomedical images by means of a digital computer to extract the desired information. But the processing here may include like visualization, diagnosis, classification, segmentation. We'll see some of the problems of the processing, and basically it can assist or automate. Yes, this will help us to automate the process, as I already mentioned, because we want to enable a system and basically called as CAD system over here. So what was the problem? Why we want this type of system? So what is the role of this CAD system, computer-aided diagnosis system? What was the problem with the manual interpretation process? So the problem with the manual interpretation process is nothing but it is tedious. So let's say you are having a larger number of images, or let's say 1,000 number of images of, let's say 50 or 100 number of patients you have collected, and it is very difficult to process all the images, even manually interpret all the images in a single day for a doctor. So that is why always manual interpretation of the images at a larger scale is very difficult. It's a tedious job as well as time consuming job, very expensive sometimes. And the most important thing is it always requires skilled supervision. You always need experts in order to decide a reliable. So the measure or the most important thing over here is the automatic detection process, and which might be preferable for fast, reliable as well as accurate diagnosis. That's what we want from the CAD system, and that is why the CAD system came into the picture. But the concept of the CAD system is not new. So it started in the early 60s. At that time, there were no machine learning techniques, because we all know those machine learning techniques always learns from the examples. We need the number of samples of the data to learn the machine. So in 1960s, it was difficult to store the data even in some computers. So how the CAD system was designed at that time by using simple low-level image processing task. But the serious and systematic investigation started in early 90s when the supervised techniques came into the picture, and we all know that the supervised techniques always require some training data, as I mentioned, that it learns from the examples from the set of data. And yes, so this machine learning and pattern recognition techniques always include the concept of feature extraction and statistical classifier that we'll see. And so before I show you something or a typical structure of a CAD system, machine learning based CAD system, I must discuss what are the advantages of the CAD system, which we have already discussed. But let us summarize once again the points. And if you can see over here the points, the importance of the CAD system. So it helps the radiologists or doctors in accurate interpretation of the images using dedicated computer systems to provide second opinions. They can verify their screening process later on. So one thing you have to remember over here, that we are not here to replace the doctors. We are here to assist the doctors, because doctors are whom will provide the data, annotated data, labeled data, and they will also give us some idea that what they want, and based on that we will design a model and give it to the doctors. So doctors will verify the screening process. So then what it helps? So it helps in improving the diagnostic accuracy. It helps in reducing or the lightening the burden of the increasing workload in this kind of pandemic situations. If you want to detect the COVID-19 by using some medical imaging technologies, so you know how many patients are affected by COVID-19. So it will definitely lighten the burden of increasing workload, and it will reduce the cancer miss due to fatigue. And the most important thing is it will reduce the inter and intra-leader variability. That's what very important is. And these are the advantages of CAD system. So this is nothing but one of the typical CAD system, machine learning based CAD system, if you can see, which composes of number of stages. And the stages are nothing but image pre-processing, ROI segmentation, region of interest segmentation, and feature extraction, feature reduction, followed by classification. These are the stages which are required to come up with a decision using ML-based, machine learning-based CAD system. So let us briefly discuss one stage, each stage. So first stage is, so input will be nothing but any medical images, and output should be maybe in terms of, let's say this is here, for example, I have taken a brain MRI images, and the output should be here, whether that person is having some brain disease or not. Like I have to classify the images into two categories, either normal and abnormal categories. So for that, if you are using some machine learning technologies or machine learning based architecture, it is called sometimes as a multi-stage architecture, because it requires it generally functions at different stages. And the stages are, as I mentioned, the pre-processing, and you all know the importance of pre-processing is, let's say there are some unwanted information present over the images, input images. So what you have to do is you have to remove those unwanted informations, maybe some noises, or maybe there are some images which are low contrast in nature. And if you not pre-process the images, what will happen is, so later on, so what you exactly want, what you really want from these images is the descriptors. So you want to extract some patterns from this type of images, or some descriptors, unique descriptors. And if you not pre-process the images, so what will happen is you may not extract those important features because of those low contrast. And if the image is also contaminated by noise, even you cannot extract those meaningful features of the descriptors from those images. And if the feature extraction methodology is that much robust, then it's fine. But if it is not that much robust towards illumination, towards noise, so what will happen is you will not able to extract relevant features from these images. So that's why pre-processing is required. So you have to check whether the images or the input images or the data is good or not. If it is not good, if it is contaminated by noise, then you have to pre-process it by using the image processing methods, whatever is there. And the next step here is, it's like optional stage, is like ROI segmentation, region of interest segmentation. So segmentation itself is an independent problem in medical imaging domain. I will also show you that how segmentation problem is different from a classification problem. But sometimes segmentation, the segmentation process is used as a pre-processing method. What exactly it says that ROI, region of interest. So let's say if you don't want to extract the features from the whole region of the image, you want to simply extract the features, you want to only focus on those regions where abnormality is present. So then what you have to do is you have to extract the region of interest from the whole image, and then you will extract the descriptors or the features from only those persons. And this is what the feature extraction is. So there are number of feature extraction methods are available in the literature. So now the question is, then how will you decide that which feature extraction method will work for your problem? So this is what the major concern in this in this type of CAD system. And the next stage is nothing but feature reduction. It's a kind of optional stage. I mean, it's why I'm calling it the optional stage, where sometimes if the number of features are less, so you did not require this stage, you can directly go to the classification stage. But if the number of features whatever you have extracted is very, the dimension is very high, and you don't know whether there are, all the features are relevant or not. Let's say if there are some features which are irrelevant in nature and redundant. So what you will do is you can apply some feature selection technique or dimensional reduction technique in order to reduce the dimension of the feature vector extracted from each of these samples. So then the final, again, the final stage is nothing but a classification stage where statistical classifiers are basically used, like support vector machine, k nearest neighbor. I will also show you one interesting article where they have reported that how many classifiers exist in the literature. It's a very interesting paper. I will show you later on. And just for now, remember that this machine learning-based CAD system always works in different stages. It requires multiple stages to come up with a final decision. And one of the most important stages over here is feature extraction and classification. And the feature, whatever we are extracting in this kind of CAD system are called as handcrafted features, because we generally used to extract the features, and the deep learning researchers used to give a name that this is called as handcrafted features. And as I mentioned that there are two vital stages in any machine learning based system is like feature extraction, hand designed or handcrafted feature extraction, and a classifier. So now the question is then which one is important? So there are, let's say, 50 types of feature extraction methods available in the literature. There are 50 types of classifier available in the literature. So then which one is important? Again, which combination is important? So how would you know that there are various types of features, as I mentioned. There are some features like edge features, local features, global features, Gabor features, wavelet features, histogram of gradient based features, and image transformation based features. Various types of features are there, and similarly there are also various types of classifiers are there. So then how will you decide that which particular feature and which particular classifier will work for your model? So that's what the major concern in this type of system, CAD system. So this is a very interesting paper. If you can see, which is already on your screen, that there is a paper called as, and the title of the paper is also quite interesting. So do we need hundreds of classifiers to solve real-world classification problem? So this is the title of the paper. Can you believe that? So and it is published in 2014 in a peer-reviewed machine learning, one of the top-tier machine learning journal called JMLR, Journal of Machine Learning Research. And what exactly they did in this paper is, the authors did in this paper is, they reported that there are 179 classifiers arising from 17 families. So there are 179 classifiers exist in the literature till 2014, and they have grouped into 17 different categories based on the characteristics like discriminant analysis based classifiers, probability based classifiers, neural network based classifiers, decision tree based classifier, rule based classifiers, bagging, boosting, ensembling, all those. So 179 classifiers exist. Can you believe it? So what exactly they did in that paper is, so they tried to evaluate or verify the effectiveness of each and every classifier over 121 data set which are there in the UCI repository, basically the data mining repository freely available in the internet. If you can you can also go through that repository and see that how many data sets are there. So what they did is, as I mentioned, that they evaluate 179 classifiers over 121 data sets, and they finally come up with a conclusion that whenever you are applying some machine learning method, machine learning technique to solve a problem, you should at least try these classifiers: random forest, support vector machine with Gaussian and polynomial columns, extreme learning machine. So extreme learning machine, maybe some of you might know that what do you mean by extreme learning machine. So so let me briefly discuss the what exactly extreme learning machine is. So extreme learning machine is nothing but a learning algorithm basically used to train single layer feed forward neural network. It has a lot of advantages over the conventional backpropagation neural network. The learning is so fast over here, and it generally doesn't fall in the local optima, and it overcomes a lot of the problems which are faced by the conventional backpropagation neural network. So if you're interested, you can go through the articles based on extreme learning machine. But the concept extreme learning machine was published in the year 2006, so it is not a new concept. So what they suggested is, so these are the classifiers you should at least try first whenever you are solving a problem using machine learning techniques. Even I also suggested the same, that these are the classifiers you should apply first initially, so before you apply some other classifiers. So that's what the summary of this paper is. And again, the question is again, so there are 179 classifiers, so then how will you decide that which classifier you will consider for your problem? So coming to the weaknesses of the machine learning models, we have already discussed, but let us summarize once again. So it follows a conventional multi-stage architecture of machine learning. So features are manually designed. So features are manually developed because we are designing the features. We are deciding that what type of features we will extract from those images, and are not updated. Very important point. The features are not updated in response to the classifier output. It's very, very important, this term. And ultimately, the selection of an appropriate feature extractor and classifier has remained a major constant, as I already mentioned. So coming to the deep learning based models, let us first discuss the advantages of the deep learning models over machine learning, if you can see, and then we'll discuss what are the difference between machine learning and deep learning, and when to choose machine learning and when to choose deep learning. And it eliminates the conventional steps of machine learning because it is called as end-to-end learning. The task will be directly learned from those images or from the data, so without the need for feature engineering, because the features will be learned here. The features will be learned directly from the images. And it's basically composed of several layers. The name itself says that deep learning. So composed of several layers that transform input data to the outputs while learning increasingly higher level features. And the most important characteristics of this deep learning based techniques are it can be easily retrained for other recognition tasks. Very, very important point. It can be easily retrained means, let's say you are solving a problem right now. You are solving a brain tumor classification problem using, and you have designed a deep learning based architecture. So maybe tomorrow your friend is solving, will solve a similar type of problem, maybe skin cancer classification problem. And so now the question is, can your friend use the same model, whatever you have designed, to solve his problem or her problem? Yes, it can. By simply changing some of the layers, it can be. That's why the name is actually, it can be easily retrained. The model can be retrained to solve a similar type of recognition task that also we'll discuss in detail later on. And the two most successful and popular types of architectures which are basically used in the domain of medical imaging are nothing but autoencoder and convolutional neural network. And the convolutional neural network is pretty famous because basically for image and video centric problems, and it is achieved significant success in several computer vision problems and also in some many medical imaging problems. So we'll see to the problems and how CNNs are useful and how they achieve accuracies or significant accuracies or performance, you can see. So the difference is we have already discussed about the difference between machine learning and deep learning, but here also, there are 4 points. I mean, the weaknesses and strengths. The strengths are indicated in plus sign, and the weaknesses are indicated in negative sign. If you can see over here. So machine learning and deep learning. So machine learning provides good results with small data sets. And if you're having small data sets, so it's better to go for machine learning. So I'll go for deep learning because deep learning requires very large data sets to provide reliable results, and this is the weakness actually. And then the machine learning models are quick to train a model, but it is deep learning models in contrast computational intensive because it is the very deep in nature, you know that, and the number of parameters are very high. So that's why, and to learn all the parameters, so it requires much time compared to the machine learning models. But coming to the weaknesses of the machine learning models, so it needs to try different features. We have already discussed about that. To try the varieties of combinations of features and classifiers in order to get the best results. But here, so we should not be worried about that because the features will be learned directly from the data, and that's what the measure the characteristics of deep learning is, and the accuracy will become constant plateaus in machine learning. If you add more number of samples, the accuracy becomes constant after some point of time. But the deep learning, as I mentioned, that it always requires large number of data sets. So the more you feed the data into the deep learning models, the more reliable result you can expect from the model. So that's why it is written the accuracy is unlimited, and sometimes it has been seen that the deep learning models have beaten even the human beings for some computer vision problems. So very interesting actually this deep learning concept is. And so as I mentioned that it always requires a large data set. So do we always is there any other way? Let's say if you are having a small data set, so can we apply deep learning methods? Yes, we can apply. There are some researches going on, even there are some papers which have been reported, and there are some ways if where you can apply the deep learning methods in case the number of samples are less. We'll see it. But here I've written one statement in red color text, which is very, very important, that there exists no large scale annotated medical image data set till date comparable to ImageNet. I hope you all have heard about this term. This is what you mean by this ImageNet. So ImageNet is a kind of data set which called initial content almost around 2 millions of images and of 1,000 categories. And because of this data, I mean this data set, so many deep learning architecture came into the picture. I will show you what are those architectures. So, but this type of data set is not available in medical imaging domain because we know how difficult it is to capture the medical images, and even the annotation is too costly. So in medical image, so this is again a challenge in medical imaging domain. So even if you will collect a data set or bigger data set, and then if you want to release it publicly, and you can also publish a paper related to that. So simply the data set also be a big contribution in this particular domain, because there, as I mentioned, there is no such data set available publicly. And so coming to then when to apply machine learning and when to apply deep learning is just check that whether you are having sufficient computational power or not, and data or not. So if you are having sufficient computational power and data, you should go for deep learning. And if you're not having that, so you can go for machine learning. But as I mentioned, even if you are having small data, so you can also go for deep learning. There are some ways. So that we'll also see later on. And this is, I will not discuss in detail about the convolutional neural network, what the layers does and this. And I will just show you that how exactly it looks like, and how the structure of the convolutional neural network is, and what it contains, and what is the role of each layer. We will discuss in brief. And if you see, there is a diagram in this particular, yeah. So this is nothing but a basic block diagram of a convolutional neural network, which consists of some convolutional layer, ReLU layer, pooling layer, followed by some fully connected and softmax layer over here. And every layer is responsible for extracting the meaningful information from those images. And the more you go deeper into the network, the more complex feature you will extract. And the fully connected layer, if you can see, and there's a convolution. This is ReLU is kind of activation function. So it is generally introduced by Professor Hinton in the year 2012, and each layer, as I mentioned, has some characteristics. And this is, as I mentioned, this is a simple CNN architecture. So later on, a lot of other varieties of CNN architecture came into the picture with some different layers, different connections between the layers. So, and even more deeper network came in the picture later on. And this is a simple sequential CNN architecture. And most of the CNN architecture always contains convolutional, some activation functions like ReLU, maybe some variants of ReLU, and the pooling layer, so downsampling layer basically. And then finally the fully connected layer, and we all are acquainted with this fully connected or dense layer, sometimes we call it as. And why it is called as dense, because every neurons in this particular layer is connected to every other neurons of this preceding layer. So fully connected, all neurons are interconnected with all the neurons of the previous layer. So finally the softmax layer helps in deciding that which class the inputs should belong to, and it will provide a probability value. And based on the highest probability value, we will decide that which class it basically belong to. So, but this fully connected layer is sometimes dangerous using so many fully connected layers. So, because these fully connected layers accommodate numerous learnable parameters. I will also discuss about that later on. So, how CNNs work, we have already discussed over here. That convolution, ReLU pooling, and as I mentioned, that every hidden layer increases the complexity of the learned image features. Very important to know. And so coming to interesting, one of the interesting term over here, that since I think 2012 we have we are talking about deep learning, CNN architectures and all this. But the concept of CNN, this deep learning, can be tracked back to late 80s. So the concept was totally old concept, and it was the person, Professor Leekon and his group. So the research actually started in the year 1980s, but it was not famous at that time. So why it has taken 2 to 3 decades to impact Bayesian community? Because of the lack of the data at that time, lack of the storage capability, and lack of the computational power as well at that time. So other researchers criticized Professor Leekon and his group that what type of algorithm you have developed. So it takes 1 month of time or 10 days of time to train the model. So CNN concepts are not at all new. So it was introduced in late 80s, as I mentioned. So that's why I've written one term over here. So it was the right algorithm at the wrong time. But later, they become the founding fathers of the deep learning architectures, along with Professor Hinton. So this was the architecture they actually developed in the year 1998. So which is called as LeNet. If you can see the architecture of LeNet, so it is basically designed for solving a digit recognition problem. So it was digit recognition problem mostly. It's a 10 class classification problem. We all know that. And the last layer always contains that many number of neurons. Let's say you are solving 10 class classification problems, it will contain 10 number of neurons, and each neuron will indicate one class over there. So from 0 to 9, so it also contains, if you look at the architecture over here, so it also contains some convolutional layer, some soft-sampling layer, pooling layer, fully connected layer, as well as output layer. So this is the architecture of LeNet, which was there in 1998. But there is a huge gap in between. So then later on, the major breakthrough actually happened in the year 2012 when Professor Hinton came up with this architecture called as AlexNet. So this is the architecture after which a lot of architecture, CNN architecture came into the picture, but this is the major breakthrough. If you can see, so there is it is very similar to this LeNet architecture, but there are some concepts which they added later on, like the ReLU activation functions. So in this particular LeNet architecture, they have used tan sigmoid activation functions, but they come up with a new activation functions, ReLU rectified linear unit to in order to establish the nonlinearity in the network, and which is the very faster as well compared to 10H activation function. And also there are some other concepts they added, and they trained the model using millions of images. Basically, they use the data set called as ImageNet, which we have already discussed. And this is how the structure of the CNN architecture of this AlexNet looks like. Convolution, max pooling, followed by fully connected layer containing 4096 neurons. And at last, as I mentioned, that the last layer should contain the number of neurons. I mean, that many number of neurons is equal to the number of classes. And here the problem was like a 1,000 class classification problem, and that's why the last layer contains here 1,000 number of neurons. So later on, several architecture came into the picture, like after AlexNet, if you can see, VZZNet, GoogleNet, then ResNet, DenseNet, MobileNet, EfficientNet, and all these architectures after AlexNet are deeper and deeper. So now the question is that I mean, is it really simple to just simply add the layers and it will be more deeper and the result will be good? It will be not like that. So I will also discuss the same thing later on. And so I would also like to show you something. Yes, this figure. So that what do you mean by this particular challenge called as a large scale virtual recognition challenge? And it started in the year 2010, if you can see, and the bar represents the error rate, and the network name, I mean the winner. Basically, it's a challenge. So challenges are happening, I mean, in computer vision, even in medical domain as well. So what exactly the challenge is? Challenge means those who are conducting the challenges, so they will release some data set. I mean, the data set means the training set. Basically, they will release to you, and they will define the problem. And this is this is the problem of large-scale visual recognition challenge. And the ImageNet classification problem, it was a 1,000 class classification problem, as I already mentioned. And what the organizers will do is they will release the data set to you, not the testing set. We all know the importance of the testing set. It should not be provided during the design of the model. So they will provide you the training set. And based on the training set, you will design your model and you will submit your model to the organizers. Then organizers will test or evaluate each of those models who are taking part in the challenges on the testing set, whatever is happening with them. And then they later decide that which model is the best model. So every year they used to decide the winners, the runners-ups. So initially in 2010 and 11, there were no deep learning models which were taking part. I mean, that's why the winners were like machine learning based models. So it is written shallow. I mean, sometimes called as machine learning models are shallow architectures or shallow models. And you can see in 2012, the AlexNet was the winner. And as you see, this is the error rate, as I already mentioned. The error rate is 16.4. So, and it was previously 25.8. So it's a very less one compared to the 25.8. And then later on, so many architectures came into the picture, and their major goal was to reduce the error rate, And some also tried to reduce the error rate along with, along with adding some more layers. Like in VZZNet, there are 19 layers, but in AlexNet, there are 8 layers. So even in GoogleNet also, there are 22 layers. So then ResNet came into the picture. So then DenseNet came into the picture. So is it that simple that you will simply add the layers and you can able to reduce the errors? So for that, actually, after GoogleNet, when ResNet came into the picture, in that paper, the authors have reported one experiment that if you simply add the layers, definitely it will become a deeper network, but will it lead to always a good performance? So that's why so I have put these two graphs. If you can see over here, just look at the left graph which is there in the left hand side over here. So the first one, I mean here there are 4 different curves you can see, but just look at these two, I mean red and sky color, a solid curve. And so if you can see over here, so these are simple networks, convolutional neural network architectures of containing 18 layers and containing 34 layers. And in the y-axis, error, I'm representing the errors. And if you can see, the 18-layer architecture, CNN architecture, is giving good performance compared to the 34-layer architecture. So that means here it fails. The deeper is the network, the plain deeper networks achieved here simple poor results. But if you look at the graph on the right hand side, so when ResNet came into the picture, so because of the residual connections, the skip connection between the layers, so what they achieved is simply the reverse one, that the 18-layer architecture with the residual connections is giving better performance than the 34-layer architecture. So one thing you have to remember, that so what I want to suggest over here is, so do not simply add the layers and simply add the layers to make the architecture more deeper and deeper, and you will think that, oh no, the more will be the layer, the more the good performance I will achieve. No, not like that. So this is why actually I put these two figures over here. So whenever you are designing some new architecture, so you have to be very, very careful. So because the more will be the layer, again the more will be the parameters, the complexity will be very high. So you have to be very, very careful whenever you are designing this type of CNN networks. So these are the 3 percentages I already mentioned, are founding fathers of deep learning. So from left, Professor Leekon, Hinton. So Professor Hinton is very famous in the domain of artificial intelligence. We all know him because he's the also developer of backpropagation neural network algorithm. So because of the significant contributions, so they have been awarded, or they won the 2018 Turing Award, which is kind of Nobel Prize for computing, very, very important. So their contribution is really significant. So slowly we are coming towards the medical image analysis problem. So this is what the background of this medical imaging, then CAD system, then machine learning, deep learning. What's the difference between machine learning and deep learning? What is the weaknesses? What are the weaknesses of the machine learning? What are the advantages of deep learning about that? When to use machine learning? When to use deep learning? So how the CNN model, the most famous architecture is convolutional neural network. How it looks like? It contains several layers like convolution, ReLU, pooling, batch normalization, fully connected, subtemax, like that. So then, and what are the architectures which are currently, pre-trained architectures available in the literatures like AlexNet, VGGNet, we have discussed one by one. And so right now we will discuss the problems related to medical image analysis and classification domain. And so before that, I would also like to discuss a very important thing, that what are the different way to use CNN for analyzing the medical images. So there are 3 different ways, please remember. So there are 3 different ways to use CNN models for analyzing the medical images. So one is training from the scratch, transfer learning, using of the self-trained CNN architecture. So let me briefly discuss one by one. So what do you mean by training from the scratch? So like AlexNet, you will design a model in training from the scratch. You will design the model. So the parameters, mostly here the parameters are in terms of weights, the filter weights, the weights in between the fully connected layers. So you will initialize the weights randomly, and then you will train the model based on the data whatever is with you. So you will train your model from the scratch. So for that, yes, this model is highly accurate, but the major requirement for this type of strategy is it always requires large scale data set. So training from the scratch is always highly accurate, as I mentioned, but it always requires large scale data set. So that means you will design the model, you will set all the parameters, you will train the model based on the data set, whatever is given to you. It's always good, but the problem is we do not have always this large scale data set in this particular domain, medical imaging domain. So the transfer learning, so coming to the second strategy over here, the transfer learning is very, very important concept. It's mostly used in medical imaging domain. And the transfer learning means the learning, the knowledge of one network, or transferring the knowledge of one network to another network for solving a similar type of problem. So let's say you want to use AlexNet to solve a brain tumor classification problem. Then how will you do that? That's the question is. So AlexNet is already been designed for solving a classification problem, but that was designed to solve a natural image classification problem. And the classification problem, the number of classes at that time was 1,000 plus, if you can remember. Yeah, so going back to this AlexNet architecture, if you can see, so it contains 1,000 number of neurons in the last layer. So it was basically designed to solve a image classification problem. It's fine, but 1,000 class classification problem. So now the question is, so can I use this architecture for solving a similar image classification problem? Yes, I can use for solving. So what I can do over here is, let's say my problem is simply is to classify the images into two different categories. It's a two class classification problem, binary class classification problem. So what I will do is I will simply replace this layer. I will simply replace the last layer, which contains originally 1,000 neurons, by a layer which will contain two neurons. So then what I will do is I will retrain the model. I may simply retrain the last layer. I may retrain the last three layers. Even I may retrain the whole layers on my data set. So the major important thing over here is I have started with some optimized weight initialization. So I'm not starting with a random weight initialization like training from the scratch. So I will start with a random, I will not start with the random initialization of the weights. I will start with a optimal weights. So it is better always to start with that, and it requires, even if you are having less number of samples, you can also use transfer learning technique. So it's better always, let's say the models are available which are there for solving a medical image classification problem, and you can directly pick up those models, and you can also use and check whether it is working for your problem or not. And the last but not the least is using off-the-shelf pre-trained CNN features. So it is sometimes not suggestible because it is very simple actually. It's like a machine learning based system. And so what this strategy says that, and it also requires less number if you're having fewer computational resources and less number of samples. So you can also use the last technique. You can simply check it that whether it is working or not. So what it exactly says that the last strategy, that this AlexNet is already designed, it's already learned for solving a problem. The model is there already. The pre-trained model is already available in the literature. So what you will do is you will simply provide your input images and extract the features from any of the layers, mostly from the fully connected layer, or maybe the last convolutional layer people used to take, otherwise the last fully connected layer. So what you will do is you will simply pass one image to the network. The weights are already learned on ImageNet dataset. You will extract the features, I mean 4096 number of features from the second last fully connected layer, and for every image you will collect one feature vector containing 4096 number of features, and later on you will create a feature matrix containing the number of samples as well as the number of features for each of the samples, and then you can use some statistical classifiers like support vector machine, extreme learning machine, or neural network to classify the samples. So this is very simple. The last one is very simple, but may not be accurate always. You have to check it. So if you're having less number of samples, as I mentioned, so please go for this transfer learning and this initially, then later you can, if you're having sufficient number of data, sufficient amount of GPU, then what you can do is you can train your model from the scratch. So that's what the summary of this particular slide. And so coming to the problem classification, so broad classification of the problems in medical imaging domain. So I'll be focusing on only two different types of problems today. So one is a classification problem, and another one is a segmentation problem. So classification is very simple. So given an input image, you have to simply label the image, whether the image is a normal image or abnormal image, and whether the image contains, you can also grade, we can also provide grading to the images, that which stage the tumor is, and like simple, it is very simple. As I mentioned, that given an image, you have to simply label that image. But in segmentation, the input will be image and the output also will be an image, the segmented image. I'll show you how different it is from classification. So with a simple example which I've taken from internet, and if you can see over here, the first one is nothing but a classification. So you have to simply classify the image into one categories. So it is nothing but you have to provide one label that this is nothing but a cat. And the third one, if you can see, is nothing but semantic segmentation, which is very, very important. And this semantic segmentation is nothing but classifying the pixels into different categories. So basically background and the foreground categories. And I will show you in how segmentation output of medical imaging domain looks like. So it is basically recognizing and understanding what's in the image in the pixel level. Very, very important. So, and I will right now show you some of the output of this segmentation. I mean the segmented output of medical images. So here on your screen you can see there are 6 images on the first row, and the corresponding output, segmented output images are there in the second row, and which are achieved by using one CNN architecture, basically designed for semantic segmentation problem called as UNet. I will also show you how the UNet architecture looks like and why it is basically used for solving image segmentation problem, basically medical image segmentation problem. And as I already mentioned, see, the output is also an image, and basically 2 different pixels, white pixels and black pixels. So you have to classify each pixels into 2 different categories, so background categories, or that or here the white pixels are nothing but the regions which you really want to highlight. And very, very important, the first 2 images are nothing but the city of the lungs, and the second 2 images are fundus images of an eye. We'll also discuss more about it later on. So when we will be talking about this diabetic retinopathy disease, and here the measure, it's a very famous problem, it's a long-standing problem. We can say it's a retinal vessel segmentation. So here you can see there are some red color branches in these images, and you want to detect. So here the measure job is to detect all these branches correctly. And it is sometimes very, very difficult even for a human eye, even for the radiologist or ophthalmologist, to detect all the vessels clearly. So this is the output of the UNet architecture, if you can see. And what we want from our model is this one. So this is what the segmentation problem is. So you have to only highlight those parts which you interested in. So very important. So this is how actually the segmentation outputs looks like, and the classification is pretty simple, as I mentioned, that given an image, so you have to simply label whether the image is a normal image or abnormal image or like that. So I will right now discuss or show you some of the current challenges in this particular field, and the challenges, some of the current challenges I have listed out here. That detecting tumor in brain, it's been a long-standing problem, as I mentioned, and multi-class brain disease diagnosis using MRI. So I will discuss this problem today also. Multi-class brain disease, classification brain diseases are of variety categories. So, and how will you decide that what type of brain disease the person is having? So given an input MRI image, and why MRI, why not X-ray, why not CT scan also. We'll discuss what are the advantages of MRI images, and we'll also discuss some of the principles behind X-ray imaging as well as CT scan imaging, and detecting blood cancer from microscopic slide images. We have seen this microscopic images before as well. And there are also some challenges in low dose 3D CT image reconstructions, breast cancer diagnosis using histopathological images as well as mammograms, glaucoma detection. Glaucoma is a kind of eye disease, basically one of the major leading cause of the vision loss. So glaucoma, it can be detected using retinal fundus images. So these are the areas where you can develop CAD systems, so the very recent areas. So where you can develop some CAD systems using cutting-edge machine learning and deep learning technologies. And there is something called as the diabetic retinopathy in retinal fundus images, which I will also discuss. As I mentioned, there are 2 different types of problems, classification, mostly classification and segmentation. So this diabetic retinopathy problem, why I have chosen is just to show you how, this is a kind of segmentation problem. It can also be a classification problem, but which I have considered is nothing but a segmentation problem. And there is something called as melanoma recognition in dermoscopy images. Basically, it's a kind of skin cancer. And the last one, which I will discuss today, is the COVID-19 screening. So how the cutting-edge AI technologies along with these medical imaging technologies will help in fighting against COVID-19, that also we'll see. So coming to the first problem, as I mentioned, the multi-class brain disease diagnosis using MRI. So let's first discuss that why we are interested in this particular in this particular problem, and what is the importance and of this early diagnosis of this brain disease. Because every day there are 500 plus new cases which are diagnosed with only brain tumor. So brain tumor is a kind of brain disease. So what are the different types of brain disease? So brain disease can be broadly categorized into 4 different categories. It's there on your screen right now. You can see that, that there are 4 different categories called brain disease. One is brain stroke, brain tumor, degenerative disease, and inflammatory or infectious disease. So basically, they've divided the brain diseases in these four categories, and the names which are written in the blue text in the right hand side are nothing but the specific disease name which are falling under these four categories. So, that's why it is very, very important. It's very, very important to early diagnose these brain diseases, and in order to preclude the severity of these diseases and improving the patient's quality life. So, to detect the brain diseases, mostly doctors used to suggest to go for magnetic resonance imaging, MRI. Why? Because it's a non-invasive neuroimaging technique and it has some advantages over X-ray and CT scan. And let's discuss in brief that how the X-ray imagings. I mean, the principle. What is the principle behind X-ray imaging? Why the X-ray imagings are the output of the X-ray imagings are always looks in the terms of white and black and white sets, and what are the merits and demerits of X-ray imaging as well as CT scan? We'll discuss. So see, the X-ray imaging, so coming to the X-ray imaging, the images which are there on your screen right now, there are two different X-ray images which I consider over here. One is the X-ray of a palm, I mean a human hand, and another one is the X-ray of a chest. So mostly the images, I think you might have experienced in your lifetime also sometimes X-ray. So the images, parts of your body in different sets of black and white, right? And why it is black and white? It is very simple to understand. This is because different tissues absorb different amount of radiation. So calcium in the bones absorbs X-rays the most. So that's why it looks white, and that's why it's basically whenever we're having some bone injuries, the doctor used to suggest us to go for X-ray imaging because it is quite easy to see that where is the fracture in this particular X-ray samples. And the fat and other soft tissues absorb less and looks gray. That's why it looks gray, because it absorbs less compared to this calcium in the bones. And air absorbs the least, so lungs are full of air, we all know that. And that's why if you can see in the image which is there below, and where the lungs looks black in color, and because it absorbs the X-ray the least, that's why. And there are the benefits of X-ray. We all know that bone X-rays are the fastest and the easiest way for the physicians to view and access the bone injuries. Very, very important. X-ray equipment is relatively inexpensive and widely available. You can also find the X-ray machines in the rural areas. That's why X-rays are commonly used and relatively inexpensive compared to CT scan and MRI, we will know. So, and it is fast, easy, as well as low cost. And there is also some risk while we are undergoing this X-ray imaging, and there is a slight chance of cancer from excessive exposure to the radiation, because we all know that X-ray is a harmful radiation. So that's why women should always inform their radiologist or the doctors or X-ray technologists if there is any possibility that they are pregnant. So it all depends upon the setting of the parameters of the X-ray machines. If mostly they used to set the low dose radiations, exposure to the radiations. So that, but still there is a slight chance of cancer. And coming to the CT scan, so CT scan actually uses the concept of X-ray, and the outputs are really very important, and it provides excellent resolutions of the different parts of the body. If you can see, a CT scan makes use of computer process combinations of many X-ray measurements taken from different angles to produce cross-sectional tomography images of the specific area of a scan subject. So if you can see, the output of a CT scan of a human brain is there, and it is in terms of number of slices, and from base to the skull, if you can see number of 2D slices, two-dimensional slices, two-dimensional sizes. So if you can combine it, it will finally become a 3D CT images. So it is again based on the concept of X-ray images. Again, there is a chance of harmful radiations. I mean, it is more expensive than X-ray and ultrasound. We all know that, and again, much more radiation, because again, it uses the concept of X-ray. So, but what are the benefits is it provides excellent resolutions, and basically it is excellent for evaluating the fractures. So coming to the advantages of the importance of the MRI scan. So but the advantages are nothing but it doesn't involve any radiations, harmful radiations, because here the concept of MRI scanning is it will use some strong magnetic field. It is based on the magnetic field, radio waves, field gradients to generate the MRI images. Yes, it provides excellent resolutions of the brain tissues compared to the brain tissues. We are considering the problem, we are solving a problem, brain disease classification problem. That's why I've written brain tissues, but any part of the tissues of the human body, it provides excellent resolution compared to CT and X-ray, and it doesn't involve any radiations, and it's really good for healthy as well as I mentioned, but that it doesn't involve any harmful radiation, so it is good for healthy as well as disease subjects. So, but the major weakness in MRI scanning is it is much more expensive and it is not widely available. But very, very important to diagnose brain diseases because there will be minute changes in the tissues in the brain, and it will be difficult for the CT. I mean, it will be difficult in the CT scan and X-ray to detect those minute changes in the brain tissues. So that's why MRI is very, very important, and also the development of the MRI, because it's a significant contribution towards this field, and because of that, so the developer, I mean the inventor of this MRI machine has been awarded Nobel Prize. Coming to the problem, so this was the theory behind this X-ray imaging and CT scan, and why MRI, why not X-ray and CT scan is basically when we're solving, I mean when the doctors are diagnosing the brain diseases basically. And so now I will show you some interesting things like what is this multi-class classification problem, why not binary class classification problem, and what is there in between. I mean, what is is there any simplicity in binary classification problem, or what we will see. So just look at the images. So 9 different images over here. From figure A to figure I. So the first image, if you can see, so what I want over here is I would like to show you the samples from the samples which have been captured from normal person or from the persons who are suffering from any type of brain disease. And only the first image, the figure number A, is nothing but the MRI of a human brain. MRI scan of a human brain in one particular angle. This is called as actually plane. In one plane, you can say it's called as axial plane, which is nothing but the top view. Actually, there are different views in MRI. So there are basically 3 views: top view, side view, back view. Coronal view, sagittal view are there. But this is basically a axial view or top view, and most of the information you will find from this view. And that's right. And the data set basically which are publicly available contains this particular axial, I mean the images in this axial plane. And the first image itself is nothing but a normal, I mean the image which has been captured from a healthy person. And all other images have been captured from the persons who are suffering from some type of brain diseases. Which type of brain diseases, that I don't know right now, because the information is not given to us. So now the question is, we have seen that varieties of brain diseases are there. Then how will you know that yes, there are some diseases in the brain, but what type of brain disease? The varieties of brain diseases are there. So that is why the concept of multi-class classifications came into the picture. We'll see later on, but I would like to show you also something over here, that how different it is, how a normal brain is different from a pathological or abnormal brain, if you can see. So these are the samples, I mean the abnormal samples I have intentionally taken from the data set, which have, whose pattern is clearly distinguishable from the normal pattern. I mean, these are the samples which has been captured from those patients who are at their later stage of their disease. So that's why it looks very different. It looks very different. And the major difference, if you can see, what you can see, even doctor used to see that whether the person is having some disease or not. So there is a symmetric figure, if you can see, X kind of structure present in the middle of this MRI image. And if any disturbance to this particular geometry will happen, so then what you can expect is, yes, there will be some kind of brain disease. So you can see all the images, as I mentioned, that which I've taken from the data set, just to show you that how different it is from the normal images. And so this is what the symmetricity is in the normal image, and any disturbance to the structure will lead to a abnormality. So coming to the multi-class, as I mentioned, that what is multi-class classification and what is the goal of multi-class classification brain samples, but there are also some challenges in multi-class brain classification problem using MRI images. So here I have shown 5 different samples from each of these 5 categories. I mean, 4 different types of brain disease, and along with one normal category. I mean, healthy persons categories, and the images which have been captured from healthy persons. So only I have shown five different samples over here. But if you can see the patterns, there are some patterns which look similar in even normal class, as well as in, if you look at the some of the samples in infectious, the patterns looks very similar to the patterns in the normal class. So we call this problem is a large class similarities. So there is a large inter-class similarity between different classes. So this is where the challenge lies in whenever you are solving a multi-class classification problem. You will find, even whenever you are solving, even you will solve a computer vision problem, you will also find this type of problem. So how to avoid this problem? So you have to develop one network, or you have to extract, or you have to extract such descriptors or such unique descriptors so that it can be easily distinguishable. I mean, whether if the problem is suffering from this large interclass similarity problem. So this is what the challenge in this particular domain is. And earlier we have also developed two deep learning models in order to solve this problem. So the first model which we have proposed in 2018, but the paper actually came online in 2020. And the major idea was to develop 2 different architecture. One is CNN based architecture, and one is stacked autoencoder based architecture. So this architecture is called as actually deep stacked RVFL. RVFL is a kind of neural network. It's basically a randomized learning algorithm for training single layer fit for a neural network. It has also a lot of advantages over the simple backpropagation algorithm which was used in conventional stacked autoencoder, and it is a non-iterative method. And the conventional autoencoders, I mean, the training of the autoencoders and the stacked autoencoders always use the iterative procedures. For that, the training time was too high in that case. So here the measure, I mean, the goal was at the time to reduce the training time without compromising the accuracy. So what we did is, so we use the concept of RBFL in order to design the autoencoder, and these are nothing but the autoencoders, you can see, and all autoencoders are learned unsupervisedly. I mean, in an unsupervised fashion, because we do not require any, the output levels in order to train those models, and in order to train those autoencoders. So that's why it is called as like the learnings in an unsupervised fashion. So, and these are nothing but called as RBFL based autoencoders. So if you want to know more about it, you can go through my paper, which is there below. So this paper has been published in Biomedical Signal Processing and Control. You can go through the paper. It's written clearly, even the code is there in GitHub account. So you can also go through the code in order to understand, and you can also apply this technique for solving similar type of problems. So the major, as I mentioned, the major idea was to simply design this architecture in order to reduce the training time while achieving good accuracy or good performance. And if you can see, but these are the RBFL based autoencoders, as I mentioned. Is basically RBFL based autoencoders are learned. The learning is very simple over here. Only the output weights are learned here. The input weights are basically taken randomly and fixed during the training. And then after getting all the outputs of these different autoencoders, so a stacked autoencoder is designed over here, stacked RBFL based autoencoders, and the outputs of each of these autoencoders, individual autoencoders, are used to initialize the hidden layer weights of these stacked layers. And finally, so once it is stacked, so finally we used one classification layer in the last one, and which is basically called a supervised classification, because so these weights will be learned with the help of the output levels. So that's why it is called as the supervised classification. And the one interesting thing in RBFL is that basically used for improving the generalization capability, and which is nothing but there is a direct connection between input to the output, because here the number of inputs are very high, and that's why we use the random mapping technique in between in order to reduce the dimensions, and then connected those outputs in different outputs. And as I mentioned that yes, we introduced ReLU and other variants in place of PANH and sigmoid. and this particular architecture also doesn't require any fine tuning, which is required in the conventional stack dot encoder. And I will directly show you the results right now. See the results achieved by our architecture called as this stacked RVFL autoencoders. And yes, they look at the training time. So look at the training time of the other competent methods, as I mentioned, stacked autoencoder, stacked denoising autoencoder. So how drastically the training time was reduced. Even the accuracy, if you can see, the accuracy was also too good. I mean, it's better compared to other methods. And there are also an experiment we conducted. So what is the role of this direct link? So this is the main characteristics of this RVFL network, that there should be a direct link between input to output. And also we have conducted one experiment to check the importance of the direct link. If you can see, without direct links, the accuracy was like something 93.33. But later when we added the direct link, the accuracy was good. But again, as the number of, if you add the direct link, the number of parameters will be high. So that's why. So there is a trade-off in between this and that. I mean, this accuracy and training time, and that's why it takes a little bit, higher training time than compared to the without link. So and again, the next table, if you can see, is on another data set. So two different data sets basically used to validate this particular method. And so even on the other data set also, we got really comparable performance, but the training time, if you look at, is really the least compared to the other methods. And again, we also proposed one CNN-based solution, to solve a similar problem. So we tried to develop a lightweight CNN architecture containing less number of parameters compared to the methods. I mean, the network which is there in the literature, and which will the lightweight CNN architecture contains less number of parameters, and also it requires less number of memory to store. So with this idea, we proposed this architecture, and this very simple architecture, as you can see, that convolutional pooling. Again, it was I think we did it in 2018, so. And convolution, then convolution pooling, and also the detail of this architecture is here only. And if you can see, it contains only 0.23 millions of parameters, and the parameters in every layer is listed out over here: that convolution, batch, normalization, ReLU, flex pooling. And yeah, so finally we found that it requires only 0.23 millions of parameters in order to provide reliable, performance. And so this is what the performance we achieved using this CNN model, which is there on the screen right now. You can see it's a very simple, as I mentioned, that is a sequential CNN architecture, simple CNN architecture. It's a lightweight CNN architecture, as I mentioned. So MD1 is actually a data set, which is a very small data set, and as I mentioned, so it's a very small data set. So in order to avoid this, the data scarcity, we have used here data augmentation technique. So data augmentation technique we have used over here in order to enhance the training set size. And if you can see, so this data set actually is a very simple data set, and the accuracy here we have achieved is ideal results we have achieved. So that doesn't mean that this model is the best model in the world and it will work on every problem. No, not like that. So the major thing is you need to test this model, whatever is there. You need to test the model on a larger data set to check the effectiveness of the model, whether it is working properly or not. So right now we have also collected some more images, more MRI images. It is very difficult to collect even MRI images. So we have collected some of the images, and our job is to again validate the same model, that whether it is working properly on the larger data set or not. So again, the limitations we have discussed about, we have discussed that limitations, the data set size is small and the model is too much sensitive to hyperparameters. So can we use some technique, which can reduce the training time of this kind of CNN architecture or not? And can we combine even that RVFL concept in CNN, RVFL concept in CNN in order to reduce the training time and other things? So that also we can think of as a future work. And so coming to the second problem, just now we have discussed about what are the challenges in the multi-class brain disease classification problem, and what is the multi-class classification problem, and how we solve a problem using deep learning architectures like autoencoder based architectures as well as CNN based architectures. So coming to a very interesting problem called as diabetic retinopathy. So diabetic retinopathy, as I mentioned, is a kind of eye disease basically caused due to diabetes. So and it is generally diagnosed with the help of retinal fundus images. So for how fundus image looks like, I will also show you, and how it is captured. For that, fundus cameras are available, and the cost is around like 1 lakh, or sometimes it is in terms of thousands as well. So, as I mentioned, diabetic retinopathy is a common sight-threatening medical conditions caused due to retinal microvascular changes triggered by diabetes. And yeah, the statistics, if you look at the statistics, so it is very actually important. So according to the International Diabetes Federation estimates, presently the global number of individuals affected with diabetes, I'm not talking about diabetic retinopathy right now, only diabetes, is 4 to 5 million, because we know it's a common disease right now. So worldwide, if you see, so the number of individuals affected is 4 to 5 million, and it may rise to 693 million by 2045. So it's a huge number, and so then 1 out of 3 individuals is estimated to have some form of DR, I mean diabetic retinopathy. So 1 out of 3 individuals is estimated. Out of 3 individuals, you can expect 1 may have some form of diabetic retinopathy, and 1 out of 10 may prone to vision threatening as well. So it is very important to early diagnose the diabetic retinopathy problem. So that's why doctors used to suggest those who are suffering from diabetes disease, so they should go for eye checkup regularly. So very important, because they may suffer from this diabetic retinopathy, which ultimately they may prone to vision threatening. So that's why diabetic retinopathy, or diagnosing diabetic retinopathy, is very important. And again, the development of care system is also very important for this, because the number of patients are very high. And the number of patients are very high, those who are suffering from diabetes. So, and how will you know that whether the person is having diabetic retinopathy? So basically, doctors used to see, I mean, the ophthalmologists used to verify the fundus images captured from the eyes, human eyes, and I will show you how it looks like. And there are 4 different abnormalities. If they will found these 4, which are written in red color text, if you see, the microaneurysm, hemorrhages, soft exudates, hard exudates. These are the 4 reasons. These are the 4 abnormalities. If any of one of them is also present, then the person may have some form of diabetic retinopathy. So we'll see how they looks like, and how will you solve the problem, and how to design a CAD system, and what is the task over here, and whether the task is a segmentation task or whether it is a classification task. The classification is simply that you have to decide that whether the person is having diabetic retinopathy or not, or whether the person is having diabetic retinopathy at what stage. So that is the classification problem. But the segmentation problem is, where is the abnormality present, right? So you have already seen it. So how the fundus image looks like, if you can see. So this is the cross-sectional photo of an eye, a human eye, and yes, there are some vessels even in the human eye, if you can see. And this is how the fundus images looks like, which is there in the right-hand side. If you can see, it contains some optic disc, blood vessels. So this and no other things are there, because it's an image taken from a normal human eye. So that's why no other abnormalities is present over here. Only there are some blood vessels as well as the optic disc. This optic disc is very important for if there will be some disturbance in the size of this optic disc, and that might lead to some diseases called as glaucoma, but we are not focusing on it right now. So we are simply focusing on the diabetic retinopathy. So as I mentioned, there are 4 different lessons or the abnormalities that may present in the fundus images, and from which the ophthalmologist used to interpret that whether there is whether the person is having any form of DR or not. So if you can see, the 2 are in the left hand side and the 2 other lessons are in the right hand side. So microaneurysms, hemorrhages. So all 4 are present in these images. Maybe there might be some images where you will find only 1 or 2 or like that, and there is something called a soft exudate and hard exudate. But see how difficult it is for even a human eye to distinguish the pixels for microaneurysm or hemorrhages in between the background pixels, because the intensity values of this particular microaneurysms looks very similar to the intensity values of the background. So then it's sometimes very difficult to even distinguish that whether there is a microaneurysm, I mean whether this type of abnormality is present in the image or not. So then again we need the help of this deep learning architectures, which can extract some hierarchical features or some deep features from those images that may help, or that may assist the doctors in order to verify the diagnosis, that whether actually that the DR is there in that particular patient or not. And so because of the difficulties in finding or distinguishing the intensity values of these abnormality regions and the background regions. And coming to the hard excluded, it looks better, right? Because it looks, I mean, some of the intensity values are yellow in color, and it is somewhat distinguishable than the background pixel. So hard excluded is a little bit easier to detect compared to all other three. So, and the problem here is a segmentation problem. And the problem is a very recent problem. It is published in a 2020 paper. It's a very high impact journal, medical image analysis. And the problem here, they have divided. Again, they have conducted, I mean, it was associated with one challenge. And in that challenge, they released the data set. And again, many people used to send their models. And here the problem is like 4 different problems. I mean, microaneurysm is itself is a segmentation problem. Hemorrhages is itself is a independent segmentation problem. So they treat all these 4 lessons as a 4 segmentation problem, and the output should look like this. Input should image in segmentation problem. Output should also in form of images, if you can see. And so the outputs of our model should be like this. I've already shown the outputs of the segmentation methods. Yes, so this is what the summarization of the table of that paper, which I have taken from the paper for Untitled 2020. So what I would like to show over here is that you see, so this table contains how many rows? 4 different rows for 4 different problems. As I mentioned, that those 4 problems, 4 different I mean lesson segmentation problems has been categorized as an independent problems. So microaneurysm segmentation is a problem. Hemorrhages is another segmentation problem. Soft excluded is another problem. Hard excluded is another problem. So combining these 4 will be an added challenge in it. But still, these, even the segmentation of these independent parts are also challenging. If you can see the results in the 3rd column, which is in terms of area under precision curve, for the microaneurysm, the output was the winner. The winner of this team is named as iFlight Tech. So, and the VRT is nothing but the fast runners up like that. And so the output, the result in terms of APUPR is 0.5017. But in case of hard excluded, the result is good, because you know that hard excluded is a little bit easier compared to other 3, and that's where the output is quite better. And but there is a lot of scope over here to achieve. And coming to the 4th column, you look at the 4th column, approach. What are the approach they use to come up with these results? And if you can see the approach, cascaded CNN, unit, as I mentioned, is a kind of CNN architecture. Every architecture, if you see, every architecture is nothing based. All are based on cascaded CNN, fully convolutional neural network, cascaded CNN, densinet plus unit. So they combine densinet plus unit in order to achieve good result. So if you can see, all the methods are based on convolutional neural network. All the winners, whatever they submitted the models, all are based on convolutional neural networks, I mean the deep learning based neural network. So I would like to simply, so what I actually want to show you is all methods are convolutional neural network. So it's very important. And yeah, so this is how the unit architecture looks like. You can see, very interesting, the unit architecture is. So it has 2 different parts, contractive path and expansive path. So contractive path is very similar to the network which I've shown over here. And if you can see, the input over here is 256 cross 256 is nothing but an image, and the output is also in terms of an image. But previously I have shown you some pictures, I mean some CNN architectures where the output was containing some neurons, right? And yeah, madam, are you there? I will take only 5 or 7 minutes to finish my lecture. I think we are running out of time, but still, I will take only 5 to 7 minutes to finish my lecture. Is it okay? Joseph, are you there? Yeah, I've got some response in the comment box, no problem. So I will take only 5 minutes, additional 5 minutes to complete my lecture. Yeah. So this is how, as I mentioned, that say unit architecture looks like, and if you can see, it's basically used for semantic segmentation problem, pixel classification problem. You have to classify each pixel into two different categories, black and white, and the white is the basically the regions which you really want, the abnormality regions, and the output, even the input is 256 plus 256, and the output is 256, because we all know that the same segmentation, the output is also an image, very important. So this type of architecture is basically used. Even later, several variants of unit architectures came into the picture. You can go through that how to apply unit architecture for solving semantic segmentation problem. So coming to the last problem, I will discuss in brief that how COVID-19 detection can be made using chest radiography images. And I should not discuss more about COVID-19 because everybody is well known about this COVID-19, how it was caused, which type of virus, and why it is called as a pandemic, and when it started, where it started, and which date is declared as a global pandemic. Everybody, I think, know. And what are the major clinical symptoms like fever, cough, fatigue, sore throat, and shortness of breath. But still, now the major hurdle in controlling the spread is there is no vaccine or officially approved to date. So that's why the problem is. And the numbers, which I should not also discuss about these numbers because you all know better than me. Everybody, people are checking. Globally, how many cases are there and how many death rolls. So then what are the areas as an AI scientist, as an AI researcher, so you can contribute to different field in order to fight against COVID-19? So what are those? One is early warnings and alerts, tracking and prediction. So these are the fields where you can work on to and definitely it will ultimately lead to fight against COVID-19. Diagnosis and prognosis, treatments and cures, and social control. So why AI has not been impactful, that much impactful? People have been trying since last 3 4 months, even we have been also trying. So why it is not been that much impactful against COVID-19? Because of the lack of the data. We all know that AI systems, all AI, all deep learning, machine learning systems always requires the data to develop a strong model or to reliable model. So the standard procedure, we all know that RT-PCR, right? RT-PCR, reverse transcription polymerase chain reaction method, and it suffers from low sensitivity, and it is manual. It's purely manual, complicated, burdensome, and time consuming. It's still a time consuming process. And the recent studies, the studies. Maybe it's not recent studies. Yes, it's been, I think, 4 or 5 months. The studies found that the effectiveness of the chest radiography images in screening COVID-19. So chest radiography images, basically X-ray and CT scan images, how or what is the role of X-ray imaging and CT scan imaging in detecting COVID-19 is very important. And even many works has been done in this particular. Even we also tried the same. I'm not sure that how much helpful it will be, but the only thing what you can do is, I don't know whether it is directly comparable to RT-PCR or not, but the only thing we can decide, the major thing what you can decide, because we all know that RT-PCR is a time-consuming thing, and the number of kits are still very less, and there is immense shortage of these kits now, and there are also some high risk in this particular type of test because the medical staffs used to take swabs and blood samples from us, used to come close to us, and it's very risky as well. So what I can make sure that yes, this particular X-ray and CT scan may be helpful in detecting COVID-19. Yes, it's fine. It has been proved that that they are detecting COVID-19. But the best thing what you can do is, X-ray is very fast, and within 10 minutes, you can, within 5 minutes also, you can get the report, and you can at least decide that whether the person can go for quarantine or not. And later on, we can also verify the same thing with the RT-PCR method, just to check whether the methods, whatever, the system, whatever we have developed using X-ray and CT scan, we can verify later on. So, compared to again CT scan is actually so the researchers have already claimed that the CT scan has better sensitivity compared to X-ray. But X-ray is widely used. Why? Because of the easy access, easily available. It is faster as well. We have seen that why X-ray is easily available and it is inexpensive as well. So that is why X-ray is widely available. But CT scan also people are using in order to detect this COVID-19. And I will just now show you the three figures that of three different chest, three samples of three different categories. One is the normal category, the chest X-ray images of normal categories, healthy person, the images taken from a healthy person, and the images taken from viral, this taken from a person who is suffering from viral pneumonia, images taken from a person who is suffering from COVID-19. So see the three different figures, and there are also some differences, and there are some radiological indications. So by which you can interpret that whether there is a COVID-19, whether there is a sign of COVID-19 is there in this X-ray images or not. So if you can see the first image of, it's nothing but X-ray image where you can easily see the lungs in black color. You can see, and you can see the border of the lungs easily. But in the second and third images, you see it's very sometimes difficult to decide, to see, to check whether the borders of the lungs, because it is pulled by some white patchy or cloudy kind of things called as bilateral ground glass opacities, and also called as pulmonary consolidations you will find over here. There's some white cloudy kind of things you will find mostly in this COVID-19 samples. And the major thing is, the major challenge in this type of COVID-19, diagnosing or extracting, you can say, the extracting the features or the descriptors is sometimes the COVID-19 samples has similar manifestations with the viral pneumonia. Yes, it is bit distinguishable from the normal patterns, that is fine. But how do you distinguish between pneumonia and COVID-19 is a major challenge over here, again, for a human eye. So, but that's a very big challenge over here. So again, people have been applying several deep learning architectures. If you can see, all are 2020 methods have been applying because there are some data sets available publicly. These are the links of the data sets available for X-ray and CT scan people are using, and to validate or to develop some models for COVID-19. And yeah, so basically it's a 3-class classification problem. Sometimes it's a 4-class classification problem. Sometimes it's a 2-class classification problem. But the major challenge, if you consider the pneumonia, because it is, as I mentioned, it is similar manifestations with COVID-19. Sometimes it is very difficult to distinguish between pneumonia and COVID-19, and the symptoms are pretty similar. We all know that. And the last. The computer vision, there are some also computer vision solutions people have been developing since last 6-7 months, that how to detect the social distancing if the person, let's say a camera is fixed for an environment, and how do you decide that whether the persons are maintaining the distance, social distance or not. If you can see the persons who are not maintaining the distances, they are detected in red boxes, and those are maintaining, and they are detected in green color boxes. So you can also give an alarm to them that you are not maintaining the distances. You have to maintain the distances. And the bird eye views, if you can look at the right hand side one, the green color dots are well maintained. The distance between the green color dots are really good. And if you look at the persons who are coming closer to each other, and they are and if you can look at the bar color eye views, and they're coming closer, and you can also warn them you are not maintaining. And the last problem with which when people have been working is the face mask detector. It's a very important thing that because you all know that this is our life right now. You have to wear mask. So how do you know that how many people are not wearing mask? And basically in this type of scene is very difficult, because it's a kind of a tiny face detection in the wild, similar problem which is there in computer vision, and very difficult because the varieties of faces you will find a lot of problems. You will find occlusions will be there, a lot of problems will be there in this type of scene. So then how will you check that whether how many persons are not wearing mask? Also you can suggest your students to develop this type of models, which you can fit one camera on the outside of in the main gate of your institute, and which can capture those images and tell and that how many persons are not wearing mask, and if that person is not wearing mask, and he or she will not be allowed to the institute, like that. So this is also another problem which people have been trying to solve using computer vision and deep learning architectures. So these are some of the the journals which I have listed out, basically related to medical imaging domain. Those who are really want to work on this area, they can go through the latest articles in this particular journals and conferences. And these conferences are actually really top conferences, top tier conferences. So please go through the articles if you really want to make your career in this particular field. So many companies are also working, like Philips and a lot of companies, Intel are also working in this particular field. Even I have some collaborations with Intel and some other companies, those who are really working in this field also. So these are the I mean the journals which I've listed out, where you will find some good articles, and you can read the latest article as well. And the major thing is, if you read this type of articles, it will be easier for you to select a problem for your particular research. So thank you so much for listening me, for for your patience, for listening me. If you are having any questions, so you can ask some questions. The question.
Participants, if you have any questions, you can ask. You can unmute and ask.
Otherwise, they can write their even questions in the comment
Yes.
box. No questions from the participant
Yes, sir,
side.
that there are
So,
no.
but, ma'am, I have written. I mean, I have sent my email ID over there
Yeah, yes,
in
sir.
the comment box, and
Yes.
so if they are having any questions, and if they want to really
Yes.
work on this type of problems which I have covered on, even maybe the problems related to this medical imaging domain, they can email me. So I will definitely reply them back, maybe within 1 or 2 days. So actually, I was not feeling well from the today morning. I'm suffering from fever, so that's why I tried my best. Yeah. So thank you so
Thank you
much.
so much, sir. Even in this condition, you have delivered us a lecture. So kind of you. Thank you, sir.
Yeah, so I tried my best to give some as much as information as possible to you, so that you can carry forward your research in this dimension also. So it's a interesting domain. It's a very interesting domain, and as I said, that very sensitive domain as well. And a lot of journals and coming, and lots of conferences are happening every year, and you can also take part in the challenges. As I mentioned, there are a lot of challenges going on in this particular domain, so you can take part in those challenges. And I can also, yeah, and I will also share. I'm currently editing one journal. So I'm a guest editor in one ICI indexing journal in this particular domain. So if anybody also want, so they can send the papers. Papers are always welcome from your side. So thank you so much once again,
Sure,
all
sir.
of you, and I must thank all the organizers of CIT, basically the Department of EC, all the organizers, for inviting me, for giving me this opportunity to share whatever I know, my knowledge, in front of this knowledgeable audience. Thank you so much.
Thank you, sir. So thank you for sharing the information about your advances in machine learning and similar with deep learning. Thank you, sir.
Thank you so much.
Sir Jai Singh, sir.
Yeah, madam.
Good
Good
morning, sir.
morning. Good morning. I am here.
Sir, we will start in another 5 minutes, sir.
Okay.
Okay, sir. Thank you.